to make sure that the board is visible. Okay, so okay, I don't want to share anything, but I'll start the presentation for now. Just a second. What? Unmirror my screen. This one.
Zoom options. Look at your.
Wow. How do you know?
So video settings.
Sure.
And then mirror my video. Turn that off. So.
That okay, sure. But wait, why? It was always on. Good. So that will be. Then the text will be. Jesus, is that like I record all the lectures with the text backward? Thank you. That's dumb. Yeah, that's for real dumb. But okay, sure. Sorry about it. But I wanted to, that's nice. Thank you so much for telling me this. Or as I say, it's completely nonsensical. Just quick recap where we are, right? So at a high level, today's topic is to learn how to create the very first process, right? We have a tiny microkernel in which we're rooted, right? In this microkernel, we have a memory allocator, which can keep track of physical and virtual memory, and we map it one-to-one. And we also agreed that I have to see if it's visible. Yeah, probably it's not. That our user address space, like if this is a physical memory, and this is a virtual, all right, so it starts from 0, goes to some number, which we pick up from grub, and grub itself picks it up from BIOS, and that's the details are described in the homework. And what we do is that we map all available memory one-to-one, and then we said our plan was to, for user address spaces, we will start mapping them in from some high enough, I don't know, let's call it user base, high enough number, something, I don't know. Pick any number, which is like 512 GBs or something, or 1 terabyte or something like this. And this means that in a practical setting, we can have a machine up to, let's say up to 2 terabytes. I mean, I did see a machine with 1 terabyte. I will use it. Never used machine with 2 terabytes, and let's assume this is a configurable number. So if you ever have a machine which has more physical memory, you will be fine. Meaning that this max can go up to this 2 terabytes, and our scheme will work no problems. Right? And it's very simple on purpose, because then it's like we map one-to-one. We don't have to flip those two portions like x86 does. And we support, in our design, we support any amount of physical memory. And the reason for that is that, remember, we track available physical memory by using this page array. Oh, sorry, I will spell it a little carefully. Page array. Data structure, which is a list. I mean, it's a combined data structure which both implements 2 doubly linked lists, one for 4 kilobyte pages, one for 2 megabyte pages, and at the same time tracks the state of each page in memory, right? Meaning that this describes the state of this page. Maybe it's special page, should never be allocated. Maybe this like some random page here will say, okay, it's a free page, and that's on one of those 2 free linked lists, right? And what I wanted to highlight is that this scheme allows us to, no matter, to support unlimited, practically unlimited amount of physical memory. Because if we put on the machine with some number of physical memory, in contrast to how x86 does it, we do everything dynamically. We dynamically allocate this page array, and we describe all available physical memory and can allocate it, right? And technically speaking, I don't see a limitation right now, because if we want to support machines with giant memories, we just shift this number, saying that we need more space to accommodate for all physical memory, right? Makes sense? So it's not that like something like super amazing happened, but this scheme balances simplicity and practicality, in my opinion. And I don't see like a huge drawback. So obviously we don't support non-uniform memory, but like Linux does, we can say, like, for us, we just treat all physical memory as the same. But if we really want to like build this extension, we can just create an abstraction of a node, and then maybe have multiple page arrays and one per node, and maybe we can have some number of like nodes we can allocate as regular static variable in Rust, and then like essentially say, well, we have 64 maximum physical nodes, or 128. I don't know how many sockets you practically can assume will be on the motherboard. Like something like 128 is probably large enough. And then essentially allocate those page arrays dynamically, one for each node. And then again, get our non-uniform memory scheme, right? Makes sense? And again, and the second limitation is that we don't really allocate small objects. But we probably can say, look, if you very like do something like that, on top of this page array, we can build something like a body allocator. And then on top of a body, we can build a slab allocator, similar to Linux. And then this one will really allow us to quickly allocate really like small objects on a heap, right? But for our purposes, everything is fine. So this is where we are. And in the synchronization scheme, which we agreed on a homework, we kind of said, okay, yeah, let's kind of use a big log for now. And hopefully we can come back maybe towards the end of the class and revise this, thinking of how can we implement fine-grained locking or not, right? But essentially, like in the end, our goal is to build on multiple CPUs, and so everything is operated under a lock, right? So that should work. Okay, cool. So this is where we are, right? And we also support interrupts and exceptions. What's important for you guys to, when you work on your homework, maybe it makes sense to implement a pager or page fault exception. So, you know, if something goes wrong, you at least get an exception with an address which you're touching. By the way, unrelated to this, there was a question on Piazza about how to debug this system. And I forgot, I tried to follow up, but maybe I dropped the ball. So do we still have a question on how to debug this?
EDB works good, but it'd be really convenient to be able to do like big studio code. You can even way to do that.
Yeah, it's actually, okay, hold on. So first of all, thank you. Like, okay, you already know the answer. So I don't know who asked the question because it was anonymous. So, but really I said our build system supports GDB, right? And what it means is that, I mean, there are two main techniques for how to debug code. One is tracing, and second is like execution under GDB with breakpoints, right? Tracing, the most primitive way of tracing is to just use print and just essentially print what's going on. And it's a powerful tool, honestly. You say, look, at least you know what was happening. You have a trace. More advanced techniques, sometimes just print is just too slow, and for whatever reason, either the bug disappears because it's some kind of a race condition, and if you start printing, it just simply disappears, and you cannot reproduce it with print. You remove print, it comes back. Just because the race condition never shows up. Like, for example, maybe there's a race condition in the allocator and you run out of memory, but if you print, then this condition never happens because the print slows everything down and everything just disappears. It works normally. And so sometimes you really build advanced tracing tools. And we did it in practice with my students, essentially. Instead of going to serial line, we just allocate a buffer in memory.
and dump our trace in some like compact format. And it's so fast, then it's just writing in memory. And then when the system crashes, at this point, you just somehow need to get the trace out. So which means that, and it depends, if you're running on real hardware, you might, inside your page fault handler, you might save the trace to disk, for example, just because you know, okay, I'm crashing and the memory will disappear. My trace is in memory, so I need to get it out. In our case, we were running under a virtual machine monitor, so the hypervisor was responsible for getting into the memory of the guest and dumping the trace, right? But it's a powerful technique. But for you, probably for this project, for this class, print is probably enough, right? Although, I mean, like, you might run into problem. And a second, so okay, like tracing / print. I mean, print is nice because you can, I mean, first of all, you can do conditional prints and like say, look, only if I reach a specific state, which I believe is incorrect, then print something. And hopefully this is helpful for the answer, right? And second, you can acutely format your output so it's easier for a human to understand. Sometimes print is not ideal because you say, look, I don't even understand. Like maybe there is a way. I mean, by the way, there should be a third way of doing it. But let's talk about GDB. So our build system from homework 1, homework 2, and hopefully you didn't break it in homework 3 supports GDB, right? So it's like just you open 2 shells, say something. I forget exactly what we asking, but make GDB or make GDB no apps. And in the second one, you just open GDB and then connect and communicate through Unix socket or something like that. And then GDB attaches to your QM or virtual machine monitor and allows you to install breakpoints and everything. So you can set a breakpoint on a main function in the kernel, or even on the start, or even on the BIOS, which runs before main. And then essentially single step through the Rust program, right? GDB itself, despite the fact that it looks like a very inconvenient tool, in practice, it's quite powerful, meaning that it has this, you can debug in both assembly, you can debug in, like it has support for source code. I don't know, when you're asking for Visual Studio, what is it you believe you're missing in GDB? You're aware of this layout split options, right, where it shows the source code and everything. And still, it's more convenient for you to do it under Visual Studio. And it's totally fine. So, hold on, but wait. So here you can do breakpoints. You can do single stepping, you can explore assembly. GDB can also stop, and you can actually type a command inside QEMU. It's a top. Essentially here in QEMU itself has a console, and you can say, dump me the state of page tables, for example. This is useful because then you know, I forget exactly like what format it supports, but it can show you like the layout of virtual and physical memory, right? And in general, the state of the CPU. So you can go into this console and ask, okay, show me what's going on. So sometimes when something absolutely weird happens, QEMU will give you an answer. Moreover, QEMU emulates execution of the CPU, right? Which means that it actually, there is a flag, and I forgot if we pass it by default or not, but if we can dump all the interrupts and exceptions. So for example, if you have a triple fault and machine is trying to reboot, you will actually have a trace of those. You have like, okay, first was a page fault didn't go through because there was a double fault resulted in a triple fault. And it will all be in the trace of QEMU, right? Because it was emulating that. So this is very useful because it will show you instruction pointer there, reasons. So you don't even have to instrument your own exception handlers with printfs. You can just get this information from QEMU, right? And GDB doesn't know it because GDB kind of like one level above. GDB, the way GDB works is that when you, like, if this is your emulated QEMU machine, then GDB runs as a process on the same system, right? And really, the GDB protocol allows you to kind of
like it goes and it walks through like kernel virtual machine KVM and whatever. If it's not running on KVM, it just talks to QEMU. It allows you this protocol between these two allows you to install like a breakpoint or like read memory. Essentially, you can dump any memory from this, right? But it doesn't know that there was an exception which QEMU injected into this system, and that's why maybe it was a timer interrupt. That's why there was a context switch, right? So QEMU allowed you to do this. And I figured maybe I forgot to what details we went into using QEMU for debugging in the x86 class, but I can probably show you how it can be done, right? So GDB, QEMU, tracing. I like GDB. I don't know. I like GDB because it can run in all the most weird environments in the world, like where you only have sometimes maybe this connection is implemented through a serial line or some serial line over IP over TCP IP. It still runs, and so you don't have to waste your time on setting up Visual Studio, right? But if this bugs you, then in the x86 class from last year, I think maybe either homework 1 or homework 2, we explain how to create a setup which allows you to use the Visual Studio with this, not exactly this system, build system, but a very similar one. So you can go there and use this setup. I don't think that it kind of almost works. So Visual Studio relies on a plugin which talks to GDB, which underneath everything is still running like this, right? But Visual Studio, I think, talks to this GDB. And sometimes it bugs, and sometimes maybe you will see something like some odd behavior, but in most cases, I think it works. I also like GDB because it allows you to like write your own tiny scripts. I mean, this is where the power of GDB comes in. And I mean, technically, the same can be done on Visual Studio. You can install those scripts actually, since you still work with GDB, so it's not a showstopper. But really, first you can use some clever scripts to like maybe the page table and dump specific mappings. But okay, if you like it, right? But what's more interesting is that kind of GDB, this instance of GDB sees this machine as a single memory, right? So it knows about the symbols of the kernel, like essentially it can translate between the source code of the kernel, between the executable like instruction point or state or value to a specific source code line. But imagine you at some point running an operating system, you start a new process and start running inside this process, right? At this point, GDB is confused because unless you tell it explicitly, it says, okay, wow, you're running in this address space, your instruction pointer points here, but really, like it's outside of the operating system kernel which you loaded at the beginning, right? And I have no idea what's going on. And there is a way to essentially hook up or explain to GDB so that every time you essentially switch the address space, load a new symbol file, and then GDB will let you know like which source code and everything, what you're running inside this address space. That's kind of cute because then like you do context switching and GDB still understands that, okay, you are on those symbols, you go back into the kernel through a syscall, you switch the symbol file, and then it knows that you're in this kernel. I'm not saying that I'm pushing you to do this because we're not going to spend a lot of time in user level, but just as a tool in your toolkit for your future use. This makes sense? But how many people use GDB for homeworks? Not everyone, so roughly half. But how did you debug? You say that you use Visual Studio.
I eventually
Print.
but
Yeah, no, I don't mind it. It's like what I'm saying is just like use one debugging environment. So just don't be afraid of using GDB. I wanted to go and say something else, but I forgot which other. Say again. TUI. No, but this is TUI. TUI is this. TUI is it's a GUI for common. What is it for command line interface, right? So like that's where GDB essentially splits your screen into like whatever source has or whatnot, maybe register if you like.
That's I like the tool, but I mean, not everyone likes it, right? I wanted to say something about it, but fine. But okay, this is that's the main approach for debugging, right? The most unusual thing, which I did not discuss a lot, is that you can use QEMU. In fact, as I was maybe mentioning in the past, sometimes when you try to configure the hardware, you don't know how to go about it because Intel manual is just not, either it's written in an awkward manner or it's not sufficiently detailed, or the details are spread all over the manual, and you fail to set up a specific flag saying, okay, like enable, let's assume, forgot to set enable super pages when early on boot and you're trying to use a 2 megabyte page, and then you get a page fault and you think, okay, why? Like everything is mapped, all the addresses, or like all the addresses are correct, so shouldn't fail. And then it's useful to take a look at the QEMU source code, or even there is a tracing facility within QEMU itself, which allows you to, first of all, if you look at the source code, you see like QEMU accept will send a whatever protection violation exception or a page fault if this flag is not set up. At least you know that it assumes that this flag should be set up. Because it's only correct to the degree to which QEMU implements the CPU specification, which also can have bugs, and different emulators actually implement CPU slightly differently, right? So none of them is absolutely correct. So it's not always work. It doesn't always work, but in many cases it does work. So reading through the QEMU source code sometimes helps. Like specifically in my own experience, when you build hypervisors, like the state which you have to configure from the very first, like even to start running, is giant, and it takes you weeks or days to understand, like, and it just exits with some obscure error code which you cannot decipher, and it's very hard to say, okay, there is no like incremental, we put into something and then something and then something. It's like all at once, and this all at once always says, okay, error. You don't know what is wrong. So, and reading QEMU source code helps. Okay, debugging wise, so I strongly encourage you to use either GDB or, I mean, all of these techniques, honestly, but GDB is probably the most powerful, and it will get more and more complex. So you should learn how to dump the state of the system. I mean, advantage of GDB over just Visual Studio. In Visual Studio, you probably can inspect a value of a specific variable, but it can be that either the variable got optimized out, or simply your state is more complex. If, for example, you say, I want to inspect what's on a stack, or I want to reason about, like the state of my interrupt stack, for example, because you were running on one stack, you switched the stack, but maybe the switch didn't go through. And in this case, GDB allows you to like dump the registers, dump the memory under the stack pointer, understand what's going on, right? So this is kind of like, this is where the power is. Okay, any questions about debugging? All good for now. So yeah, it will become more and more kind of urgent. But okay, but back to the topic of our lecture today. What I want to get to is to discuss how we can start the first process, right? So like our recap, we have the memory allocator. We know how the user memory will look like. It starts from this user base. How can we start running user code here? So if you were building this kernel, how would you do this? Let's take a sec. Most talkative guys are gone. So these two rows are gone. So now it's your turn. Like, don't be silent. There is, like, again, in this cloud, there is no such thing as being wrong, like there are so many ways to build it. And first, second, of course, the cloud is also open-ended, so there is no like, okay, no right way to think about it. Fork a process, okay. I mean, that's a good, I mean, I appreciate this line of reasoning. You say, look, I know that processes are created with fork. What fork does in a classical Unix system is that it's a system call, which when it gets into the kernel, it just clones this address space, kind of like makes another one which is identical to this one, right? And it returns and starts running here exactly at the same location in the child. And the only difference is that in the parent it returns PAD, and in the child it returns 0, right? Okay, will it help us? Like, let's think about it for a sec. Like, again, we're talking about the first process, right? So in order to fork something, that something has to exist, right? So we might, like, if you already have this process 0, then fork will allow you to get the process 1. And I'm not saying that fork is a bad idea for cloning the processes. We'll talk about it more. I kind of claim that it's maybe not the most interesting or maybe not the most useful idea. But we can build fork in our microkernel if we want. But we still need this process 0. How can we go about it? And alternatively, I can rephrase the question if you remember how xv6 does it. How does xv6 create a very first process?
Well, I mean, you have to first load the binary from this to maybe some memory for this allocated.
I actually agree with you. So let me like repeat it for everyone. What your classmate just said is the following. We can, if we have a disk driver and we have a disk, we can create an address space. So here in the kernel, we will have a data structure, which will represent our process. We'll have a pointer to the page table, which will describe this address space, right? We already know how to implement this page table because we discussed how to build page tables, right? Address spaces. You know, that's our next homework. We're going to learn how to do it, right? And then we're going to load some pages from disk to memory, right? Somewhere here. And and maybe it's an L file. And then we will implement maybe a tiny loader in a kernel, which loads this L file. It really takes an L file and loads some, parses the ELF and loads some section of this ELF, which is like a text section, data section, CSS. Then don't forget, we set up a stack. And then we start executing from the entry point, right? That's what you said. What's the advantages or what's the problem with this approach in our current microkernel? Like roughly speaking, what is missing? What don't we have? What is it we don't have right now? And what is that? Let's agree on what to build.
We need a way to
Correct. So I agree. So let's sketch how we want to do it as well. So if we are in our main function, we did a bunch of initialization. I don't know, like init GDT, init interrupt. We did something like whatever, init memory allocator. We haven't done it yet, so working on it. Like this is homework 2, right? This is homework 3. And at the end of the main, we can introduce another, not system call, but just like function call in the microkernel, something like create. Well, I don't know. Yeah, we can call it process. I don't know. Let's call it process 0. Like, I don't know. In those systems, like this very first process is always 0. So we will
implement something like
create process 0. And inside this,
like, let's be concrete. So tell me what will be inside this
create process 0. What is that we need to do according to this outline?
You read it, parse it out. Load all those things.
Correct. So what I want to do is like I want to create an address space. Let's create address space. Read L file and maybe like and load L file, which might involve some relocations, but maybe not, hopefully. We'll see. Right? What else do we need? Well, oh yeah, by default, yeah. So when we create an address space, okay, that's a good comment. So how do we specify a privilege level? How do we say that this will run with user privileges? Anyone remembers? Say again? Yeah, so how do you switch to ring 3? And when do you switch it? Okay, so that makes sense to maybe postpone it, but let's just, I mean, I don't want, because otherwise it's a huge detour, but it makes sense. Like in 2 minutes, we will talk about ring 3. But just to make sure that this picture complete, when we finish our kernel, essentially imagine it like it creates some data structure P, which is a process, right? How do we want to end this main function? And I kind of like thinking, let's end it similar to how x86 does it. So it was imagine we created this process, somehow did all of it. How do we start running P? It's similar to x86, let's just not invent. Do you remember?
Is it exec or schedule to that process?
Schedule. So how do we do this? And what does it mean? Like in your own words, explain how we start running. Like at some point, we want this instruction pointer to point to the entry point and say that the text section of this process, right? So how do we achieve this? There are multiple ways, but like at the very end of the this function, we want to call a function which we will call something like a scheduler loop. In x86, I forgot what it was called. Maybe it was called schedule or something, right? Roughly speaking, that's an infinite loop, which will go through a list of all processes in the system. In our system, like starting from some global variable. In our system, only one process on the list will be this P, which we created, this create process 0, right? But at this point, imagine maybe we will need to do some more initialization here. Maybe we'll start other CPUs. But if we get to this loop essentially will take a look at this process, right? And it will switch to it, which we'll talk about what does it mean to switch. But at some point, and this is where, okay, let's think about for a second, what does it mean to switch? Now we'll probably, I'll probably just trace this one for a second. Continue. What does it mean to switch? Like what does it, what happens in this scheduler when it says, okay, I figured out the next process to run. What is it I want to do?
Stack.
We should probably talk, like, we will talk more about it. Right now, we're running on some stack, which we created maybe in the bootloader. Maybe we reinitialize the stack early in the main function, right? But roughly speaking, this new process P0 will have its own kernel stack. P0 will have its own kernel stack, right? And so, like, maybe deep inside this scheduler function, after we pick the process, we can say something like switch. And this switch will take, I don't know, like, doesn't matter what it takes, but it will take a pointer to this stack. And at this point, it will never return, like if it entered the switch on this stack, it will not return on this stack, but it will like switch to this stack and will start running on this stack of the process P0, right? And at this point, the stack kind of controls the future of this P0. If, for example, you somehow on this stack will encode a computation which just runs in an infinite loop, this P0 will never start running, right? So its stack is kind of the future. So it's a continuation in a way, right? And so, but since we control this stack, we can figure out what to put on this stack in such a manner that it should lead us at some point to an IRET instruction. And this IRET instruction will remember, if you remember how we talked about interrupts, like remember the very first 5 things which hardware expects or saves on a stack when it enters the interrupt. And the same IRET essentially expects that these 5 things are here. One of them will be instruction pointer, right? One of them will be code segment. One of them will be stack pointer, SP and a stack segment. And there will be also E flags or R flags, right? So these 5, if this instruction pointer points to right here, IRET will essentially start executing here. And agree with this? Does it still make sense? And at this point, I wanted to come back to how do we switch back into ring 0 or ring 3, sorry. IRET allows you to switch between the rings. So when we start executing IRET, before IRET, we are in ring 0, running like in this main, reach the switch function. And then we started executing on the next stack, but switch still didn't switch the ring, right? And at some point, most likely the way to do it is to wait until IRET is at the very last instruction executed in the kernel, which will take these 5 arguments, and how do we switch into ring 0, or into ring 3, sorry. You will remember? Not very hard, so like somehow it escapes you. Mind. So, okay, what are these 5 things? Which one of these will control the ring? R flags, stack segment, stack pointer, code segment, instruction pointer. CS. Good job. And SS as well. 2 of these, right? Because remember, and okay, what do we need to put there to switch into ring 3? Your
descriptor.
Oh, wait, not exactly. You probably you're right when you're saying it, but let me just reiterate it. Someone earlier in the class said, in the GDT global descriptor table, we'll create different entries, right? Entry 0 is this default unused entry, but we will create a code segment for the kernel, which will be privilege level 0, stack or data segment for the kernel with privilege level 0. But we also will create code and data segments for the user and for the data segment for the user with privilege level 3. So essentially, these 2 entries, while we're running in the kernel, we're using these 2 entries, code segment and data segment with privilege level 0. But the one which we put here on this stack, both of these stack segment and code segment, will point to this code segment and data segment with privilege level 3, right? One of them is executable, one of them is like readable, writable. That's why we separate them, right? And at this point, this IRET instruction will really switch the ranks, right?
Make sense? And this is what x6 does, and we might do something slightly different, but at least that's a reasonable kind of outline of how to get to running into in a ring 3 in the process address space. So again, just make sure that I wanted to recap everything. So we started from main, homework 2, set up interrupts and exceptions. Where if I ask you why are we doing this, like how is this setting up interrupts and exceptions is needed for this today's lecture or today's and tomorrow's? Why is it so important for us to set it up?
We need the interrupts.
Correct, because the way we I read it into this user code, some number of cycles passes or time passes depending on how you configure the timer, but this timer interrupt will be delivered and we'll transition back into the kernel, right? And we'll go back to this context switch and go back to the scheduler loop, right? So then we initialize memory allocator. Memory allocator is important because in order to construct this address space, this page table, we need to allocate memory for the page tables, right? And of course, now we are building this create process 0, right? And we kind of know the outline. So if we create the process successfully, which means that there is an address space, we loaded some elf, we maybe relocated this elf a little if we need. And then by the time we exited this function, this process will be on some list of processes. And then we enter the scheduler at the very end, and then we will switch to the process from this list, right? That's our plan. And that's kind of like a running kernel. Okay, let me come back to this. Remember, before we started talking about it, Manvik said fork. Well, fork, like this is what we really need. So it's like, let's be concrete. So it's not just a fork. And then someone else said, okay, let's load everything and stuff like that, right? So we don't really need fork for now. But maybe inside this first process, if we want to create process 1, then we can either build fork, or I kind of argue, let's build something like and create process system call. And it will just, instead of just cloning the address space, we'll configure more carefully what should happen with this new address space, right? Maybe it's a better abstraction compared to fork, because really often fork is often followed by exec, so which means that you first clone the address space and then throw it away. It's a little wasteful, and also fork is a little hard to support, but this one is easier. So you don't really need to do like copy of the address space. Okay, let me stop here. Any questions about? That's the outline. So we all understand the outline for now, right? We want to build it, right? With these 3 steps, what is missing? From what? IOPIC, make sure that we can talk to disk, or okay, so that's a good question. So, and this is what I was trying to get to. So you told me that we want to create an address space. Sure, we know how to do it. We already have functions for that. But then you said, okay, let's read the L from disk. And the question is it the most is it the simplest way to go about it, to read something from disk? In order to read from disk, we also need a file system, which is a little like we either have to build a file system, or we have to somehow have a special chunk of the disk, which is some special simpler file system, or some kind of like whatever, just a blob of elves or something. But maybe like is that the way to go? Like, first of all, like remember, we're trying to build a microkernel, which means that we would ideally avoid having a disk driver in a microkernel, and ideally we would like it to run as a user process as well. Because if there's a bug inside, it doesn't propagate into the kernel, it at least like stays safe. Like, most likely the system stops working, or maybe at least one disk in the system stops working. But then at least the attacker cannot own the entire machine, right? Because they were sitting here, and that's the bug which they found, right? So my point is that first, and second of all, it's just simpler. You don't have to build a disk driver. You just like ideally. So the question, like, can we get away without building a disk driver in our scheme? And how to do it? Again, always the simplest possible approach.
You pass like a fixed address to the function, like,
Fixed function, fixed address, but like still, imagine we have like L for this process. I don't know what we call it. Let's say we call it init. And like we want to read L of this init, but it has to be somewhere.
Machine just rebooted, right? So sure, that's a good idea. So how would you preload the entire binary in the memory, into memory? You know, there are multiple ways, like some of them are dirtier than others. Like you can say, look, and then this is what, again, back to x86. Do you remember what x86 is doing? How do they, like, it's not even init. Init actually, they read from disk because they do exact. But before init, they have a tiny little trampoline, which they start, which kind of they just instead of like they read it from somewhere into the memory of the very first process, and it's just a handful of assembly lines which execute exact, and then exact reloads the address space. So where is that trampoline? Where do they store it? The most don't remember. They like, again, there are multiple ways to go about it, but they just simply say, look, we'll compile it as part of the kernel. Like this is like essentially your init sits. Remember, we have control over the linker script. We can create a section, or just like forget about it. Let's just put it inside the data section. Like it's like a long string of something. So it's a long string of bytes, and it like this contains your process, right? Make sense? That's the way to go. And it's like, again, you can play with those tricks. Like in x86, we can pick up from their build system how to label the beginning of this elf, the end of it. In their case, it's not even elf. They just use the binary code because it's like 5 assembly instructions which set up the stage to execute exec. We can do the same trick. So we can, in fact, like try to go the same route and have a very small trampoline which creates a process. But then we still have to pass something to this create process. In case of x86, they just pass a string exact or whatever, / exact, but it means that the file system is already there, and I want to avoid the file system. So that's one way. Let me suggest to you a slightly cleaner way. We have a powerful, I mean, there are advantages and disadvantages of this approach. Advantage is that we say, look, since we're booting on top of Grub, Grub does understand file systems. I mean, Grub is like it's an operating system which is way bigger than the one which we're building in this class, right? They don't implement context switching, if I understand correctly, maybe they do. But it's a very capable piece of software which in fact understands a bunch of file systems, right? So Grub, as part of this functionality, it says, okay, by the way, I can not only load the kernel itself, I can also load additional modules, multiple, and like Linux boots, and Linux boots the kernel, and what's the typical module which the Linux kernel brings with itself, right? Do you remember? Did you hear about initrd? Initrd is a file system which essentially, it's like, because maybe the kernel itself doesn't know what to do next, it doesn't have a file system, or maybe not in all cases it may have a working file system, but then this file system comes as a module booted by Grub. It has like all the loadable kernel modules and stuff like that. Like additional modules can be loaded into the kernel to extend it with support for additional file systems. So, but like roughly speaking, so there are two parts: the kernel, Linux kernel itself, and a file system which describe initial Linux environment. And then just switch the file system to a real root, right? Do you guys know this? Anyone? Did you hear about it? Okay, cool. So we can play the same trick. We say, look, let's use grub, and we will introduce the kernel itself, and our module will be like essentially, well, again, we can play different tricks, but let's just assume that it's an L file of this very first process which we're trying to start, right? Make sense? That it's easiest in a way that I'll show you in a second that it's easy to create the build environment in which this L is linked. Then you write a grub command, and this is loaded as a module. And from inside your kernel, since we talked about this start info data structure, and right now we only picked up the layout of physical memory, but in a very similar manner, you can pick up the additional modules. And grub faithfully it loads the kernel here in memory, and it will load the additional modules somewhere in memory too, right? We'll probably have to play a trick to make sure that our end symbol does not overlap with this module, which might be a little tricky, but nevertheless, that's the way to go, right? So, but alternative ways like compiling this entire DOM0 into the kernel is also a viable option. So under what conditions you want to compile your domain 0 in the kernel itself? For example, you're not booting on grub. So some people in this class said we're gonna put on top of UEFI. Similar thing can be done in UEFI, but different plumbing will be needed. So, but like if you want to unify it and make everything simple, then just compile your ELF into your kernel, and the grub or whatever the other bootloader will boot it there, right? Make sense? Okay, so, and then meaning that from this main function, you will be able to kind of like load, I forget exactly what grub calls it, start info, and from here you will be able to get your domain 0 ELF, right? Load start info is passed as an argument to main. In this homework 3, we're extending our bootloader with support. I don't know if you read the homework instruction, essentially. If you had a chance, so it's I think it's inside the EBX register. And so we pass it inside the main as a, no, we actually don't pass it inside the main. We just save this EBX register in the start info variable, global variable, right? And then we can initialize it, get the address of this vault, and at this point we get the L file in memory, right? And so, as you were saying, so essentially the trick here is that we solve the problem of a file system and a disk driver. We just rely on the grub to say, look, yeah, we trust you have a file system loaded in memory. So we at least can read this ELF. And at this point, if we create if we do know how to create the address space, this address space, right? Then we can start loading this ELF into this address space. Make sense? So if I ask you a question, we're almost there, but we need to load this address space, this ELF into this address space and make sure that it runs in this address space. What's involved in this step? How do we make sure that we take an ELF, which was generated by the compiler, and load it in the address space? Remember, we also agreed that the address space starts at somewhere here, user part of the address space. Let's call it user base. And we want to load it, we want to load the text section here. There will be an entry point, there will be some other sections. We'll create a stack, set a stack pointer, and we will, when we do the IRAP, the stack pointer will be correctly initialized. The user will start running using this stack, right? And this instruction pointer will be initialized with the entry point of the program, right? But yet I wanted to get more details from you. What's involved? Get an ELF file. how do you even generate this L file? With what flags and how? No, like at least maybe sketch the problems which you're facing. So you can't just like at least the envelope of those problems which you have to solve. I agree with you, compile, right? We just need to make sure that the stuff which we compile satisfies a couple of invariants. What are those invariants? And again, it's an open space, so that you can go different ways about it, but just at least again figure out the simplest way. Do we?
Related to the section.
Yeah.
We have
It's called relocation. That's one of it, but okay, hold on. And yeah, you're right. So this is what I was looking for. So we maybe need to relocate the boundary or binary, or we need to generate the binary in such a way that it does not need relocation. So like both options are viable options. Do you guys remember which route x6 takes?
it has yes.
Yeah, hold on. When you think about these things, don't think about specific flags, just like think about the property. So one property is that we can use the compiler in such a manner that whatever, like, first of all, what's inside this L file? Do we still remember roughly? We don't have much space, but I will use it here. So what is an L file? Do you guys remember at all? But you're fresh out of x6 class, right? Let me quickly share my screen to make sure that I recorded a little. And just a quick refresher on ELF files, right? So at a high level, ELF is just a container file, right? And it has a header, which is well-defined, well-known. It sits at the very beginning of the file. And from there, from the header, if you read the header, you read the magic. You say, look, it's really an ELF file. And in order to load the file in memory and start running it, ELF implements two different views of the file. And it's labeled here with blue and with green, right? So roughly speaking, the green part allows you to just pick up the data from the file, which might contain multiple sections. Like there might be an init section, a text section. Those are all executable sections. So in green, we label everything as just executable. So essentially you say, look, I will take this section, load it in memory, create the page tables will be created with executable flag. And then the entry point should be in one of those sections. And by the way, the entry point is pointed right from the header as well, right? Okay, sure. Then the next section, actually it's called segments for historical reasons. And the next segment is writable data. You just copy this into memory, get your data section in memory, configure the page tables, read write. Then the next segment is read-only data, so you configure the page tables read-only. Typically, those are page-aligned, but sometimes not. And there are some additional sections. For example, the SS section is not saved on disk; it's just described segments, right? It's just described, and you just like create enough space in the every space of the program, and just fill it with zeros, making sure that it's initialized correctly, right? So that's one view. This is used for loading this thing in memory. And it's possible to compile Rust program. And in fact, I think we did it with the kernel itself. We just said, okay, make sure that our kernel is ready to run at a specific address. We pick this address here, which is first megabyte. And then grub just did exactly the same. So it read the ELF file of the kernel from the file system like followed, open up the header, and there is a specifically, it's a table, which is called a program header table. A pointer from the header to the program header table, which contains pointers to all these green sections. And essentially just loaded all of them and then just blindly trust the compiler and our build system to make sure that everything is loaded at 1 megabyte and above, and then it passes control to the entry point and then everything runs, right? So all the addresses in the code, when you essentially have a move instruction, will have an address of something 1 megabyte, I don't know, plus 15, for example, right? So instead of like having this address to be set like 77 megabytes, because maybe 77 is not even mapped, or because we didn't create a page table which map it, right? But the compiler and the linker ensure that the addresses are, that the binary is relocated to run at the first megabyte. Make sense? So it's completely static binary, so there are no dependencies on anything else, meaning that we do not expect to load any shared libraries or anything like that, right? Because everything is there. So we just, and that's the invariance. Those are the invariants which I was trying to bring up, meaning that yes, if you use a compiler, like typical Rust, no tricks, like exactly how we did for the kernel. We did it already once, but now we kind of like need to do it in a nested manner, meaning that we will take the domain 0, compile it into a separate binary. And one way to go is to make sure that it's statically linked binary, which is relocated to run at which address. We want this code to just be ready to run in our new process. What's the relocation? What is the relocation address which we have to pick? Oh, can we pick something like here? Around the first megabyte. Yes, no. Who votes for yes? No. Everyone votes for no. Okay, why no then? Huh? Great question. Is it in the virtual? Are those virtual addresses? This one is not virtual. It's your code is running, right? So like I picked up one assembly instruction from your text section. I picked on purpose a move instruction with some address. Which address is this? Huh? Why is it physical? No, it's important. Like, and I mean, I appreciate the question because, you know, wait, first of all, we don't really know which address. It depends on how we set up the environment, right? But the intent is that we will early on boot, even before we started running, grub switched into 32-bit mode, which means it enabled page tables, and we continue running on page tables. We switch into 64-bit mode, and we're running on a 64-bit page table, which means that like we can play weird tricks and say that, okay, the process will run in real address space, which is totally non-trivial, but probably possible to implement somehow. But really, since we're creating the address space, which is a page table, we will like this will be executed on top of this page table, right? So all these addresses in the program will be a subject to translation. So you take virtual address, go through the page table, get the physical address, and the physical address can be like anywhere, somewhere here, physical memory, right? So it's important to understand that those addresses are virtual. On the other hand, I said, okay, maybe it's not set in stone. If you suddenly use this piece of code before even switching to the protected mode of execution, meaning you're still in real mode, no segmentation, no paging, then it's real addresses, right? So it depends on how you configure execution environment, right? But a safer option is to, just as a rule of thumb, is that all addresses are virtual, because it's very exotic to build system in which you stay in real addresses, right? In the worst, like, but we get the point. So this is a virtual address, right? So then what if we want this binary to run, this L binary, like in the virtual address space of the process, which address do we have to pick as the relocation address?
Just somewhere in the
Somewhere in the user space, and what are those addresses like?
second half.
Correct. I agree with you. So, and this is there. And like just make sure that I mean, maybe I'm phrasing the question in such a manner that it's hard to answer, but really we said, okay, the lower part of the address space is reserved for the kernel. So you can choose this address to be anywhere in the upper half of the address space. It would be a little odd to just randomly choose it, right? So I suggest let's pick the user base just to make sure that, you know, we start immediately. We remember this address when we start debugging, we know that it's a well-formed address, and we see that, okay, if we are executing somewhere around this address, it means that we are executing user code, right? Makes sense. So essentially, yeah, so something like a user base will work, right? Okay. So back to your idea. So we just say, we take the compiler, take the build script and a linker script, and just make sure that it's completely static binary, kind of similar to how we compiled the kernel itself, like no std, because they're like, obviously it's no std because there will be no standard library unless we want to build our own, which we might build parts of it, but let's say no std, whatever else. And also, like you say, no position independent code, and everything is just statically linked. And it's a bundle ready to run on this user base address. Then we simply get it from the grub. Very simple code to load it into this address space, and we're ready to go. Make sense? So, and this will allow us to start the very first process, right? The second part of the L file. Okay, first, let me stop here. We still have like 2 minutes. Any questions about this? Just wanted to make sure that we understand that we started main, create process, we create address space, we read it out, we chose to read it from memory because it was loaded there by grub. We loaded elf, just simply hoping, like following this protocol, following the green lines into the address space of the user address space. And roughly speaking, we only have to set up the stack and create this trampoline on this stack to make sure that when the scheduler is fixed, when the scheduler picks us up, we can exit from the kernel into the user space, right? So, and then this will be, the first process will be ready. Make sense? Any questions? Say again a word, I missed the word. Yeah. Yeah. Yeah, every time, and I'll come back to it, but like this line, create address space. So every time we create a new process, we'll create a new address space. And for simplicity of the code, it will contain two parts, similar to how x86 does it. The kernel part of the address space, all of this kernel memory, all available physical memory, right? We also will map always one-to-one. And then the user part of the address space can stay empty for now. But every time we start reading ELF and loading something, at this point, we'll allocate, depending on how large ELF is, we'll allocate page, like essentially we'll map some pages, right? And those pages, the physical pages will be, of course, from this region, right? Because we will get them from memory allocator, but we will map them consecutively in the user part of the address space, right? And we'll do that because when you do a syscall, then you don't have to switch the address space, but just continue, you can continue to operate on this on the same page. So it's very similar to how x86 does it, like follow the same path. Okay, any other questions? I'll come back to it next time. I'll show the code for how to compile your kernel, make sure that the grub is there, like how to implement this module. What else? We'll set up this stack And we will talk a little bit about relocation possibly, although I don't think it's strictly needed, but there is a way to compile this binary as a standalone binary, but still allow moving it in the address space. So we can quickly touch on that because real kernels will do this relocation step, making sure that you can actually, you're more flexible and you can load more additional elves, like specifically, not just the main function of the program, but also like those loadable shared libraries or DLLs on Windows, right? So let me stop here. So that will be our homework number 4, so essentially create the first process. And then we'll talk about syscalls, meaning that this guy can invoke the syscall back into the kernel. And then we'll talk about scheduling and context switching, which means that syscalls will allow us to create new additional processes, and a timer plus scheduler will allow us to switch from one process to another. And at this point, it's kind of like a meaningfully complete kernel, which you can run on your whatever, on your device. Okay, let me stop here. So thank you. I will then see you